Hello, well in this problem we got two parts to it. Firstly, we're given that the matrix A is skew-symmetric. You've got to think about what that means again. And also it says, suppose there is a matrix Q where Q is e to the A. So suppose Q is the matrix e to the A, and I want to show that Q is in fact an orthogonal matrix, which is a nice result. So firstly, A is skew-symmetric. So that means if you take the transpose of A, you get minus A. So that's the first thing we have to note there. Now Q is equal to e to the A, and I want to show Q is orthogonal. So to show that a matrix is orthogonal, we have to consider Q transpose Q. And we hope to get the identity matrix out of that. So that means substituting this in, this is e to the matrix A, which is a matrix itself. We're going to take the transpose of that, and we're going to multiply by Q. Now please be careful with your index laws and things here. You cannot just somehow pull these in or do anything with this. This is a matrix and I'm taking its transpose, so I've got to be careful with what I mean by that. So I'm just going to go back again to the series and expand things out in series. So e to the A is the matrix sum I plus A squared times 1 on 2 factorial plus A cubed times 1 on 3 factorial plus and so on. And all of that has to be transposed. And then I'm going to multiply that by the matrix 1 plus A squared times 1 on 2 factorial plus A cubed 1 on 3 factorial plus and so on. Now when you transpose a sum of matrices, it's just the sum of them all transposed. So you transpose I, you get I. You transpose A transpose becomes minus A. So just notice that. I take the transpose of this matrix, I get A transpose is minus A. Take the transpose of that one, I get the transpose of A squared. Well, if you take the transpose of A all squared, you just get back to A squared again. So it's A squared times 1 on 2 factorial. When you transpose A cubed, again you're going to get minus A cubed 1 on 3 factorial plus and so on. All that multiplied by A plus I plus A squared times 1 on 2 factorial plus and so on. Now this matrix here, this is just e to the minus A, and the second one of course was just e to the A. Now because A commutes with itself, as we saw, we had a little theorem that if you've got A to the B, A to the A, so e to the A times e to the B, and the A and B commute, then you can just combine these together. And so you get A minus A. And of course that means it's e to the 0 matrix. And if you shove the 0 matrix into the expansion, you just get I. And that means, therefore, I can say Q is orthogonal. So that's rather nice. There's a way of constructing orthogonal matrices. You just take any skew-symmetric matrix and you raise e to that power and you'll get an orthogonal matrix. The second part's a little bit harder. It says you find a Q so that there's no skew-symmetric matrix with Q equals e to the A. So you've got to cook up a Q so that this equation can never happen. So how do you think this through? Well, often when you're dealing with matrices, think back to the analogues back in just ordinary arithmetic. If these were numbers here and I said, how would I find A? Well, I would take the log of Q. Yeah, just in ordinary arithmetic. If these were real numbers, I'd say, well, A is the log of Q. So I want to cook up a Q that hasn't got a logarithm in some sense. And so you think, well, what numbers can't I take logs of? And the answer is, because of course, negatives. So why not put, as an attempt, I'm going to show it works, but why don't we try putting Q to be the analogue of minus 1? So I'm analogously trying to take the log of minus 1, which we can't do in the real world. So in this matrix world, I'd be trying to take the log of minus the analogue of minus 1, which of course is just minus I. So that's my guess. It just says find a Q so that there's no symmetric matrix that works. Now I've got to show that it actually really doesn't work. So what do I do with this? Well, I use my part A. So if there were a skew-symmetric matrix A such that Q equals e to the A, then that would mean Q is orthogonal. That would mean Q is orthogonal. So that would mean then, if Q is an orthogonal matrix, then that would mean e to the A is equal to minus 1. Sorry, minus I, because Q is minus I. Okay, so I just plug that in. I get e to the A is minus I. Now, look at the traces of each side. So the diagonal elements of e to the A have the form e to the lambda I, where lambda I is an eigenvalue. So that would mean the trace of e to the A is a sum of expressions with e to the lambda I, which are always positive, and so they would always be positive. But if you work out the trace of minus I, well, that's going to be, whatever it is, it's going to be, well, it's going to be minus 2, which is negative, and that's impossible. So the trace of this one has to always be positive, and the trace of this one, which is supposed to equal it, is always negative, and that's impossible. So that means I found a Q that there is no A, so that Q equals e to the A. Otherwise, we have a contradiction. And that's the solution to the problem.